All right, let's get into it. What if I told you that our planet has kept a diary, a detailed logbook written over millions and millions of years, recording just about everything that's ever happened? Well, it's real, and it's written in stone. We call it the fossil record. So, when you hear the word fossil, what's the first thing that pops into your head? For a lot of us, it's probably something huge, right? Like the massive skeleton of a T-Rex you see in a museum, just towering over you, a real giant from a lost world. But just hang on to that image for a second, because what if the really big stories, the most detailed histories of our planet, aren't told by those giant bones at all? What if they're told by clues so tiny you could fit thousands of them on the tip of your finger? That's exactly what we're going to dig into today. Okay, so first things first, let's make sure we're all on the same page. What even is a fossil? The official definition is pretty straightforward. It's the remains or traces of ancient life. Now, remains are what we usually think of: bones, teeth, shells. But the word traces, well, that's where it gets really cool. A trace could be a footprint left in ancient mud, a burrow an animal dug, or even fossilized poop. It's literally anything left behind that says, I was here. And here's the thing. These fossils aren't just scattered around randomly. They're neatly organized in layers of rock, like pages in a history book, creating a timeline that we can actually read. And what early geologists figured out just by looking at these layers is pretty amazing. They saw that the deeper you dig, the older the rock, and the simpler the life forms you find. As you move up toward the surface into younger layers, you start to see more and more complex organisms appear. And then, every once in a while, you find a layer just teeming with life. And then the next layer up is almost empty. A sudden, dramatic disappearance. That's a mass extinction, written right there in the stone. It's the story of life, chapter by chapter. But it gets even better, because fossils don't just tell us when something lived. They're like little postcards from the past, telling us exactly what the world was like back then. Just think about this for a second. Let's say you're hiking and you find a fossil of an ancient coral on top of a mountain hundreds of miles from any ocean. What does that tell you? It tells you that spot wasn't always a mountaintop. It used to be a warm, shallow sea. Every single fossil is like a clue that helps us piece together what these ancient worlds actually looked like. So can we take this even further? Can a tiny fossil tell us not just about its own little corner of the world, but about the climate of the entire planet? The answer is a huge yes, but to find it, we have to think really, really small. And for that, we're heading to the bottom of the ocean. Scientists can drill deep into the seafloor and pull up these long tubes of sediment, called cores. And packed into that ancient mud is what you could call Earth's microscopic logbook. The little authors of this logbook are these guys, foraminifera, or, we can just call them forams. They're these ridiculously tiny, single-celled organisms. But here's what makes them so special. They build these beautiful, intricate little shells for themselves using the elements that are floating around in the ocean water. And if we zoom way, way in and look at just one of these tiny shells, smaller than a grain of sand, we find something incredible. This little shell holds the entire history of Earth's massive ice ages. So how on earth does something so small tell a story so big? Well, it all comes down to some really clever chemistry. You see, these forms act like tiny, ancient thermometers, and the secret is hiding in the oxygen they use to build their shells. Okay, stick with me here. In the ocean, there are two main types of oxygen atoms that matter for this story. There's the normal, common kind called oxygen-16, which is lighter. And then there's a much rarer, heavier kind called oxygen-18. And the only thing you really need to know is this. Because it's lighter, oxygen-16 evaporates more easily than the heavy stuff. So, let's picture what happens when the planet starts to cool down, like at the start of an ice age. First, water evaporates from the ocean's surface, and more of that light oxygen-16 goes up into the air. Then winds carry that water vapor toward the poles. It falls as snow. But because it's an ice age, that snow doesn't melt. It just piles up year after year, forming giant glaciers. All of that light oxygen-16 gets trapped in the ice, which means the ocean that's left behind has way more of the heavy oxygen-18 in it. And this is where our little forams come back into the picture. They're not trying to do anything special. They're just floating around, building their shells out of whatever oxygen is available in the water. They are perfect, unbiased little record keepers of their environment. So the connection is incredibly direct. When scientists find a forum shell that's packed with that heavy oxygen-18, they know for a fact that it lived during a cold glacial period when tons of ice covered the poles. But if they find a shell with a more balanced mix of light and heavy oxygen, they know it lived during a warmer period when all that ice had melted back into the ocean. By analyzing millions of these tiny fossils layer by ancient layer, scientists can create this stunningly detailed chart of Earth's temperature going back millions of years. These tiny fossils are literally an ancient climate thermometer. So, from enormous dinosaur bones to microscopic shells, the fossil record tells one epic story. It shows us that our planet has never been static. Its climate, its environments, and its life can and do change in dramatic ways. Which leaves us with a pretty big question. What can this diary from the deep past tell us about the chapter we're all writing right now?